Hello, I'm Mark Kimsey, Director of the Intermountain Forestry Cooperative at the University of Idaho in Moscow. Looking forward to talking with you today about the role of geology on forest health, nutrition, and productivity here within the Pacific Northwest region of the United States. Wish I could be there with you in person, but at least glad to have the opportunity to talk with you virtually. Today's presentation is give you a 30,000 foot view of the diversity of geology in this region. It's composed of metamorphosed ancient seabeds, flood basalts affected by continental glaciation and volcanism, batholiths, island arcs in the accreted terrain. A very fascinating geologic region, to say the least. And then we'll touch on how all the properties, the mineralogical properties of these different geologies are drivers of forest health, nutrition, and productivity, and the controls of soil, topography, and climate in building out models that allow us to make management decisions for creating and maintaining resilient and productive forests in light of stressors that face our forested ecosystems. Before I get started and providing an overview of the regional geology, I just want to state that I'm not a classically trained geologist. So for those that are in attendance here in person or virtually, I might elicit a smile or two, or maybe even a grimace in some of the terminology that I use, kind of from a layman's perspective. But I also do appreciate this field and this broad and rich field of geology, and I consume as much of this information as I can to help improve our research in forestry, as it is the foundation for the forest health and productivity of our systems. So with that disclaimer in place, I'll just jump into this regional map that you see on the screen. And without going too in depth, just look at color patterns. And you'll notice that in the central and the northern portion of this regional map, there's quite a diversity of colors relative to other regions in this broad footprint that we call the Pacific Northwest. For those that have some knowledge of this region, this encompasses the states of Washington, Oregon, Idaho, western Montana, western Wyoming, and northern portions of California, Nevada, and Utah. And so we're going to dive into what those colors really mean to us from a forestry perspective for the rest of this talk. We'll start this overview of geology with what we call the belt supergroup. These are metasedimentary in origin. They were formed from sediments deposited in an ancient seabed located here in the northern Idaho, northeast Washington, western Montana, and stretches up into British Columbia. These ancient seabeds were laid down with different energy deposits. So low energy deposits typically were going to be silt or clay-sized fractions, leading to siltstone, claystone, and then once metamorphosed into siltite and argillite. With higher pulses of energy, coarser grained material was laid down, typically sand-sized grain. That once that metamorphosed, we get what we call quartzite. These beds of quartzite, siltite, and argillite have very unique characteristics mineralogically relative to other regional geologies, and we'll touch on that import on forestry in the following slides. West of the belt supergroup metasedimentary geology, we find a well-preserved basalt plateau formed from what they call the Columbia River flood basalts. It's a region that covers roughly 210,000 square kilometers. This basalt plateau can reach to depths of 3,500 meters, composed of hundreds of layers of these different flood basalt deposits. You can kind of see that in the stair step fashion there in the upper left-hand picture. They can be meters in thickness. They can be tens of meters of thickness. Um, each one of them would rapidly cool on the Earth's surface, forming fine-grained mineralogies. They're primarily mafic in nature, so that has import when these soils weather. They tend to be fine-grained, a smaller particle size class, and more iron and magnesium rich, all of which has bearing on the forest health and productivity of the region. One of the major factors in shaping our landscapes and our soils of the region is a result of ice, continental glaciation to be precise. Uh, in our region of the Pacific Northwest, our northern tier was probed by the Cordilleran ice sheet from British Columbia and Alberta. These lobes that would come south, extending roughly about 100 miles, would be often up to several thousand feet in thickness. Um, the till that would be carried with it would be of mixed mineralogy and is often quite different in mineralogy relative to the local geologies upon which the till was deposited, creating for a very complex system for us in forestry. Another fascinating feature of these lobes would be these giant ice dams that would form in these riverine systems of the Rocky Mountains, backing up these giant lakes, two of which you see here, the Glacial Lake Columbia, Glacial Lake Missoula. And during periods of global warming and retreat of these continental glacier lobes, these dams would fail. And when they'd fail, these massive flood events would occur where these lakes would drain very rapidly with a lot of energy and creating what we call the channeled scablands of eastern Washington, a very fascinating region if you ever have a chance to visit. So ice has been an important player in shaping the landscapes and then also contributing to the complexity of the mineralogy and soil development of our region. Other events that have shaped this region as a result of plate tectonics and specifically the western seaboard of North America is an active subduction zone between the Pacific plate and the North American plate. And Cascade Range that extends from southern British Columbia to northern California on this western seaboard of the United States has multiple volcanoes of varying activity. The most recent was a fairly major eruption from Mount St. Helens in 1980, I think one, covering a good portion of eastern Washington and Idaho and into Montana and Wyoming. And you can see that with kind of the orange AOI in that middle graphic. You can see that there was other eruptive events that were much more massive, attributed primarily to the Yellowstone eruptions and the Long Valley eruptions. All of that material has either eroded or been or buried long since. The one that shapes what we see today from a vegetation component perspective and its influence on our landscapes is the eruption of Mount Mazama, also known as Crater Lake, which is the image on the top right. That's the remnants of this mountain. This eruptive event is what they call a circular ring fissure eruption. Lost about 4,000 feet of its dome. About anywhere from 80 to 120 cubic kilometers of volcanic tephra were ejected. If you could cover the entire state of Oregon with about 45 centimeters in depth with that amount of volcanic tephra. As you get closer to Mount Mazama, you'll often see that picture on the kind of below Mount Mazama or Crater Lake there. You'll see that deep pumice. You'll see these deep pumice deposits that can be meters in thickness. As you get more distal, you become more aeolian deposited. And this would be your finer silt loam textured soils with very differing properties than their brother pumice. And we'll talk about what this means from a forestry perspective in some following slides. But volcanism, along with continental glaciation, has transformed our landscapes that we see today. I'll wrap up this broad overview of geology with a brief mention on the Idaho batholith. It's an igneous formation stretching from North Idaho down into central Idaho, primarily composed of granite, granodiorite, tonalite, some orthogneiss, very different in nature to Columbia River basalts, primarily felsic relative to the mafic Columbia River basalt mineralogies. We'll talk about some of the other features that are of import in soil development and their impact on forestry here in a few slides. The other one that I'd like to mention is the secreted terrain. Idaho was beachfront property at one point in time. We have the old continental North American plate that approximately is most of central and southern Idaho. And this western suture zone is the boundary where these island arcs come slamming into the old continental North American plate and creates what we call this accreted terrain. And it's fascinating when you're doing geologic road trips with students and you're going down one of the highways that follows that suture zone, and you can see the differing geologies on one side of with the accreted terrain and this old continental North American plate geology on the other. So very fascinating and complex, but that's what gives joy to forest management in this region, is trying to capture that complexity. So why do we want to try to understand that geologic complexity? The next couple slides, we're going to talk about why mineralogy matters. Our ancestors knew it well. They are the ones that discovered dirt. And I like to start out when I talk with my students about the role of geology in forest management. And I show them these two pictures, stand 1 and stand 2. And I ask them, do you see a morphological difference between these two forests? And after some minutes of hemming and hawing, they'll come up with statements like, well, I see some dead trees in stand 1. The color looks a little different. The tops seem a little bit more rounded. Maybe some stunted growth in the foreground of stand 1, and then they'll look over at stand 2, and it's a different green. It's a deeper color of green. The trees tend to be more pointier. There looks to be maybe a little bit more density, many more stems per unit area in stand 2 than in stand 1, and I'll say good observations, and there's a reason for that. The stand 1 is on what we call weathered quartzite. Again, this is that metasedimentary material from the belt supergroup. Again, quartzite is just essentially sandstone that's been metamorphosed. Stand 2 is sitting on a deep volcanic ash cap. This is that Mount Mazama ash that we talked about earlier, over a calc-silicate gneiss. And whenever you see that term calc-silicate, it just means there's some carbonate, there's some calcium in that soil, or that soil parent material from particular rock type here called gneiss. Whenever you have calc-silicate, it weathers deeply. So these soils not only have the advantage of the ash cap, they also have a rock that weathers deeply, and that's important from water holding capacity, nutrition, etc. So let's talk numbers. We've been talking about the Columbia River basalts, the Idaho batholith granites, and the belt metasedimentary rocks of the region, and the story all comes down to silica. As you go from the metasedimentary soils to the basalts, as you can see, the silica content decreases. When you're in those quartzitic soils, whole rock geochemistry can often exceed more than 80% silica content. And by definition, as silica content increases, all your other oxides, like your iron oxides, calcium oxides, magnesium oxides, are going to decrease. And that impact on forests and forestry in this region is well illustrated in this figure or this picture in the lower right-hand corner, where we see trees growing on siltite argillite and a shrub or a grass field growing on quartzite. Again, that comes down to water. Oftentimes in this region, it's about water. Those quartzitic soils have shallow soil development, typically are coarse fraction in nature, have large particle sizes, have very low CEC, low water holding capacity, which creates very challenging and stressful conditions for forests. Whereas the siltite and argillite, even though they are metasedimentary as well as the quartzite, they're primarily a sand or a silt and clay sized particles when they weather. Therefore, they're going to hold more water. They may not have as high a CEC or a water holding capacity as say some of our other soil types, but more so than quartzite. And so this factor of both particle size and then silica content is really what drives a lot of our forest health and productivity related questions and needs in this region. And you can see that relationship in these graphs and soil available P and CEC on the left-hand side of the slide, just showing how different soil parent materials have different chemical characteristics. Those chemical characteristics are important relative to the forests that are being sustained by them. You'll note that most of the elements that drive different biological functions in our forests come from the rock. And so as the quality of that source improves, by default, the forest health and productivity of those systems would also improve. It's also driven by the species demands for nutrition. I've got a picture of a granite forest on top of a western larch forest, and just looking at that granite forest, you see a much more dense foliar canopy, more stems per unit area than if you go down to the western larch forest. You see very sparse and thin canopy in a western larch forest, and not surprising, the grand fir or a true fir forest type will have very high nutritional demand as opposed to a western larch, which will have fairly low. So understanding then the role of species demand relative to nutrition supply by our soil parent materials will lead to or aid in during reforestation or silvicultural activities where species selection is important. You can select species that are appropriate for the regional soil parent material. I've frequently brought up the concept of water availability is important in our region that's typically faces Mediterranean or continental climate related summer droughts. Volcanic ash greatly impacts our forests in a positive way. The mineralogy of volcanic ash is primarily composed of glass, which weathers to short range order minerals called alpha and ferrihydrite, all of which have high surface area. And that high surface area allows volcanic ash soils to often have 2 to 3 times more plant available water than, say, a more coarser textured glacial till or granitic sandy loam soil that you see in these images. Very critical in our particular region. And just to end on a modifier of the effect of geology or some source of soil parent material on forest health and productivity is topography. Topography is also driven by the geologic formations of the region, but topography also imparts aspect and slope which defines water retention, or solar evapotranspiration patterns, which drives which species might be present on one landform versus another. And so it's something we have to be cognizant of and include in our modeling, is these aspects of topography and how it modifies climate and soil parent material influence on forest productivity. So we'll wrap it there. In the next slides, we'll talk about how we develop models that help us make management decisions appropriate to these landscape features. And in the end, it's harnessing big data. It takes a collaborative network to get access to thousands and thousands of records that allows us to start to tease apart these complex interrelationships of climate and geology and topography. So we, develop this network that says, all right, we can build this inventory data network. All of it is geospatially located. We can start tying those plant records to environmental drivers like climate, soil, and topography. We might ingest in some remote sensing products to help aid in the quantification of these features. And then we go into very complex computational modeling to start to define and explore these relationships. And ultimately, we want to be able to predict outputs that allows us to come up with thinning recommendations or risk ratings, and or these what we call bias corrections for our current growth and yield models. And so it's big data, and that big data is only capable when you're working with many organizations across the landscape to be able to capture these complex relationships. And when you're modeling these forest attributes, the days of linear regression are over. We can use things like deep learning to uncover these relationships, where we build these training data sets, and through ensemble methodologies and machine learning techniques like gradient boosted machine learning, deep learning, we can come up with kind of almost what we call meta learner algorithm that can take multiple different machine learning models, compute a mean model from that to provide a prediction. And that prediction allows you to capture things like what we see here in the variable importance diagram, all the different site and stand characteristics, and then eventually get a prediction. And those predictions, when I first started getting in this world of machine learning and seeing predictions of 80 and 90%, on validated and independent data set predictions, I was blown away at the power of these different machine learning, deep learning models to uncover these complexities. But it's doable. And that then allows us to develop things like what you see here. We have developed forest carrying capacity models for the Northeast, Southeast United States, and the Northwest. And essentially what these models allow you to do is to anywhere inside these kind of colored dots, you can pick an AOI and you can predict the maximum number of trees of a certain size can be carried on that landscape. And why is that important? Once you know a maximum, we know that typically to avoid mortality, you operate or you manage to 60% of that maximum. So that threshold is critical in defining that maximum and the thresholds that then come with that. And what's important is that these are climate driven as well as geology driven. And by being climate driven allows us to ask questions like what will happen on these different geologies and landscape positions if climate changes and gets warmer or drier or cooler or moister. And we did that for the Northwest, and that little histogram you see down in the lower right-hand corner essentially shows that while the distribution on the low end of maximum carrying capacity stays relatively similar, we lose the high end. And roughly we were seeing about a 5 to 20% reduction in forest carrying capacity across the landscapes in various situations. And so having these ability to model climatic conditions as well as other drivers allows us to role play what we may have to do in the future to maintain resilient forests. We can then wrap all these models into these apps and tool sets because at the end of the day, we want the forest manager to be able to use these models. So we develop these online web app carrying capacity calculators. We have a Jupyter notebook, Python coded app that anyone from a forest biometrician to a forest manager can utilize and capture the effect of site, which is your geology, your climate, your topography on forest carrying capacity relative to some species or stand dynamics that you're interested in maintaining or shifting within some management footprint. To conclude, I just want to give a shout out to our stakeholders that are supportive of the research that we do in our region. Without them, it would not be possible. It's a public-private tribal continuum partnership over time, and we just thank them for their support. With that, I'll conclude. Just thank everyone for listening to this presentation on regional geology and environmental attributes that affect how we manage our forests in this region. Invite anyone here, if you have an opportunity, to come to Moscow, Idaho. I'd be more than happy to give you a little tour of the region so you can get to experience the diversity of and the excitement that this geology brings to our region. And thank you again for the opportunity. Wish I could be there. Look forward to your presentations.